Alright, so today we are going to learn section 4.4. Solve the differential equation using a given substitution to reduce differential equation into one of the previous three types of equation. So in this section, it is not difficult, it is very easy. So the question will give us the condition for us to do substitution. Alright, so firstly, let's recall what we have learned in the previous three sections. So section 4.1 again, okay? So we learned separating variable method, okay? Separating variables method. So the pattern is dy by dx equals fx times gy, okay? And in section 4.2, we learned that the type of the question is one side of the differential equation can be written as derivative of a product. Okay, so this one can be written as the derivative of a product. All right, so this is type 2, and type 3 is similar to type 2, but we have to multiply an integrating factor to make it to be the equation of type 2. Okay, so this form is dy by dx, please remember, okay, plus px, okay, and times y equals qx. All right, and if we multiply an integrating factor, so e to the power of p, the e to the power of the integral of px, okay, and times dy by dx, I think it is not enough space, so I just write, okay, so I just write this step. We just multiply an integrating factor, okay. Okay, so please remember, okay, multiply an integrating factor, okay, to form a new equation, and this one belongs to type 2, okay, type 2. So this is what we have learned before, all right? So now we are going to learn this section using substitution. All right, let's look at example 10. So the question gives us the substitution, okay? We substitute z equals y over x to transform this equation into a differential equation in terms of z and x, okay? So then by solving this new equation, find the general solution of the original equation giving y squared in terms of x, and sketch the particular solution curve passing through the following points, okay? So now let's see. So because here we use substitution, okay, and finally the equation should be in terms of z and x, okay? So it means that we should replace, okay, dy by dx to dz by dx, okay? So because we have to replace y, okay, in terms of z and x, all right? So using the given condition, z equals y over x. So in order to replace dy by dx, so we have to write the subject to be y equals z times x, okay, z times x. And then now we dy by dx, okay, so dy by dx, it means that, so dy by dx equals dzx by dx, all right? So it becomes dz, using product rule, dz by dx times x plus, and then keep z, and then dx by dx, which is 1, okay? So it becomes this one, okay? So it becomes z only, okay? So we express dy by dx in terms of z and x only, okay? And now we can replace dy by dx by this term, okay, by this term. So we can have, so we have x times dz by dx plus z equals x squared plus 3y squared over 2xy, and here we can also replace y in terms of x and z, all right? So here is x squared plus 3, and y is in terms of x, z times x squared, and 2x and then times x times z, all right? And continue to simplify it. So it is x squared plus 3x squared z squared over 2x squared z, okay? And we can cancel the common factor x squared. So finally, it is 1 plus 3z squared over 2z, okay, over 2z. And also we can continue to simplify it. So it will be 1 over 2, it will be 1 over 2z, and then plus 3 over, or maybe we can keep it, okay, we can keep it. And then, so we can get that x times dz by dx plus z equals 1 plus 3z squared over 2z, all right? So we move z to the right hand side, so it will be x times dz by dx equals, so we simplify it, so it is 2z here, and 1 plus 3z squared, and then minus, okay, minus here, it should be 2z, it should be 2z squared, okay, it should be 2z squared. So finally, it will be x times dz by dx equals 1 plus z squared over 2z only, okay? So now you can see we can use separating the variables method, okay? Because you see we can separate the variables, okay, here. So now it is easy to solve the differential equation. So it will be 2z over 1 plus z squared dz equals 1 over x dx, all right? And we do integration, okay? Do integration, so 2z and then 1 plus z squared dz equals the integral of 1 over x. And then here for the left hand side, so for integration we have learned integration by substitution, integration by partial fraction, and also integration by parts. And here we just use integration by substitution. We can let the denominator be u, okay? But here I don't choose the way. I can write as 1 over 1 plus z squared and then d, because 2z, okay, 2z if we input into d, so it becomes z squared, okay, z squared, and continue. We can also add 1 here, okay, add 1, make it as 1 plus z squared. It is also the same because d1 is 0, okay, and equals the right hand side. And so now we can regard this as u, okay, so it is 1 over u du, so actually it will be ln absolute value of 1 plus z squared equals, the right hand side is ln absolute value of x plus constant c, okay? And because, okay, because 1 plus z squared greater than 0, x is greater than 0, so we can remove the absolute value sign, so it becomes ln bracket 1 plus z squared equals ln x plus x, okay? So we can simplify our answer, okay? So simplify our answer, and it will be ln 1 plus z squared over x equals c. And then by the definition of ln, it becomes 1 plus z squared over x equals e to the power of c, okay? E to the power of c. So you can let a be e to the power of c, so a greater than 0, so it becomes 1 plus z squared over x equals a constant a, okay, equals a constant a. And finally, because the question requires us to giving the answer in terms of y square and x, okay, so giving y square in terms of x, okay, so now we should replace z in terms of x and y. So we can get 1 plus z will be y over x, okay, square over x equals constant a, okay, equals constant a, and simplify it, so it will be 1 plus y squared over x equals a, all right? So simplify it, 1 plus y squared over x squared equals ax, and finally we multiply x squared, so on both sides, so it will be x squared plus y squared equals ax cube, okay, ax cube. So finally y squared just equals ax cubed minus x squared. So if you, actually you can also take out x squared, so it becomes ax minus 1, okay? But you may not write the answer in this way, okay? So you can just write this step, okay? Keep the final answer in this one, okay? So this is example 10, okay? Example 10. And one more thing, the question requires us to sketch the particular solution curves passing through the following points, okay? So it means that if you do substitution, and then you can find, okay, if you do substitution, and then you can find the specific solution, for example, okay? For example, so when I write here, okay, when, any space, all right, here, so when x equals 0.5, y is 0, okay, y is 0, so y is 0, so we do substitution, okay, we do substitution, so y is 0 equals 0.5 x squared, okay, x squared, and then the equation is x squared, so 0.5 squared times a times 0.5 minus 1, okay, so it means that this one is 0, so a 0.5a 0.5a minus 1 is 0, so a just equals 2, okay, so the equation will be, the specific solution will be y squared equals x squared times 2x minus 1, okay, minus 1. So actually you can draw a table, okay, you can draw a table to sketch the figure, okay, draw a table choosing some points, okay, choosing some points to sketch the figure, or maybe you can use, okay, you can use software, okay, to sketch it, or maybe you can choose some points, okay, use a table, okay, x, y, and calculate some points and then sketch the rough figure, okay. So this is example 10. Example 10. And now let's look at example 11. Okay, example 11. So use the substitution z equals y to the power of negative 1 to transform the differential equation into a differential equation in terms of z and x. Okay, so firstly, we do question A. Okay, so we should replace dy by dx in terms of z and x. Okay, so firstly, we should use the given condition and write, okay, because, okay, so because z equals y to the power of negative 1, so y just equals z to the power of negative 1, okay, we should write y as the subject, so dy by dx equals dz to the power of negative 1 by dx. And how can we simplify this one? It is because this can be regarded as a composite function. The outside function is something to the power of negative 1, so it becomes negative 1 z to the power of negative 2, and then d the inside function, so d the inside function is dz by dx, okay, dz by dx, okay. So now we can do a replacement, so we can get negative z to the power of negative 2 dz by dx plus x, so y will be z to the power of negative 1 equals x times z to the power of negative 1 to the power of 2, okay, to the power of 2. So it becomes negative z to the power of negative 2 dz by dx plus x to the power of x times z to the power of negative 1 equals x times z to the power of negative 2, okay. And we can simplify it, so we multiply z square, okay, z square on both sides, so it becomes negative dz by dx plus x times z equals x, okay, equals x. And after that we can write it as we multiply negative 1, so it becomes dz by dx minus x times z, okay, equals negative x, okay. So this is the new differential equation in terms of z and x, okay. So this is question A. And question B. So B, solve the new equation using an integrating factor. Okay, so if you want to use integrating factor, so the equation must have a special pattern. Okay, so it should be okay. So here you see it is dz by dx minus x times z equals negative x. So you see how the pattern is dy by dx plus px times y equals qx. So here y is z. Okay, in this question y is z. So here you see that px equals negative x. So the integrating factor is e to the power of the integral of negative x, so which is e to the power of negative 1 over 2 x squared. Okay, negative 1 over 2 x squared. Okay, so here we don't need to add constancy as we have proved before. Okay, so it is not necessary, but in calculating indefinite integration you have to add constancy, but here we don't need to choose. Okay, we don't need to choose the constancy here. Okay, it is not necessary. Okay, but formally in calculation we should add. Okay, so this is the integrating factor. Okay, so now we multiply the integrating factor. Okay, multiply the integrating factor, so we can get e to the power of negative x squared over 2 to the differential equation Alright, so now after that it becomes the type in section 4.2. So one side can be written as the derivative of a product. Alright, so obviously the two functions should be e to the power of negative x squared over 2 times z. Okay, times z. Okay, times z, and then by dx equals negative x e to the power of negative x squared over 2. Okay, over 2. Alright, so you may check whether it is true or not. Okay, actually it is true. Okay, so dz and keep e to the power of negative x squared. And for the other one, keep z, and then d e to the power of negative x squared over 2. So it is a composite function. We have this one, okay? And then d, the inside function, is negative 2x, okay? 2. So here we cancel, okay? We cancel over 2, okay? So it is true. So now we can write as e to the power of negative x squared over 2 times z equals negative x e to the power of negative x squared over 2 dx. And then we do integration on both sides. Alright, so the left hand side is very simple. So it is just e to the power of negative x squared over 2 times z equals, and right hand side actually it is not integration by parts. Okay, it is not integration by parts because here it is x squared. Okay, so it is not integration by parts. So how to do? So actually we can input, okay, move x into d, okay, and then it will be very simple. Okay, it will be very simple. So it is just move negative x now. Okay, so it is just e to the power of negative x squared over 2 d negative x squared over 2. Okay, so d negative x squared over 2, it is just negative x. Okay, it is just negative x. All right, so it is exactly to be negative x, so we can just move negative x into d to be negative x squared over 2. Okay, so now regard this is u, this is u. Okay, so it is just the integral of e to the power of u. Okay, so it is like this. So actually it becomes e to the power of u, okay, so which is e to the power of negative x squared over 2 and then plus constant c. Okay, so here it is e to the power of negative x squared over 2 times z. Okay, times z. So finally z just equals, okay, z just equals, we multiply e to the power of x squared over 2 on both sides. Okay, we multiply this one, so it becomes z equals 1 plus c e to the power of x squared over 2. Okay, so finally we should replace z in terms of y and x. So finally, okay, this is question B. Solve the new equation only. Okay, it means that we don't need to do substitution in by y and x, but in question C, find the general solution of the equation giving answer in terms of y and x. Okay, so part C. Okay, for part C, I use black color. Okay, part C. So because z equals y to the power of -1. Okay, so we can get y to the power of -1 equals 1 plus c times e to the power of x squared over 2. So finally, take the reciprocal. So y equals 1 over 1 plus c times e to the power of x squared over 2. Okay, so this is the final answer of question C. And now let's move to example 12. Okay, example 12. So for example 12, the question requires us to use the substitution u equals y minus x to transform the differential equation into a differential equation in terms of u and x. So by first solving the new equation, show that the general solution of the original equation may be written in the form like this. Okay, so now let's see. So finally, we should write the answer in terms of u and x. Okay, so because u equals y minus x, so we should write the subject to be y. So y equals u plus x. Okay, so dy by dx equals du plus x by dx equals du by dx plus 1. Okay, plus 1. All right. So now we can do a replacement. Okay, so it will be the left hand side can be replaced by du by dx plus 1 equals, and as you know, here it is y minus x. Y minus x is u only, so it will be u this is left hand side. It will be u plus 2 over u plus 3. Okay, so we transform the differential equation in terms of u and x. Okay, and now we are going to solve the differential equation. Okay, so firstly, let's move constant 1 to the right hand side. Okay, but actually you see this question we may try to use the previous three types. Okay, separating variables method. The second method is one side can be written as the derivative of a product. The last type is integrating factor. Okay, so maybe we can try the first one first. Okay, so but you see that here we have a constant 1. Okay, obviously it doesn't belong to type 2 and type 3. So firstly we move 1 to the right hand side, so becomes du by dx equals, okay, u plus 2 over u plus 3 minus 1. Minus 1, it will be u plus 3 u over u plus 3. So finally the answer is 2 minus 3 is -1 over u plus 3. Okay, so now you see that the new equation belongs to type 1. We can use separating variables method. Okay, so it becomes u plus 3 times du equals -x times dx. Okay, so now it will be very simple. Okay, it will be very simple. So we do integration, okay, on both sides. Sorry, here it should be -1, not x. Okay, it should be -1, no x there. Okay, no x there. Okay, it is -1 only. Okay, so now it will be 1 over 2 u squared plus 3u equals -x plus constant c. Okay, -x plus constant c. And finally, we can replace u by y minus x. Okay, so we can get 1 over 2 and then y minus x bracket square plus 3 times y minus x equals -x and then plus constant c. So I would like to multiply 2 first because I don't like fraction. Okay, so it will be y minus x bracket square plus 6 y minus x equals -2x plus 2c. Okay, plus 2c. Now we do expansion. So y squared minus 2x actually, for the final answer in your textbook, it just it doesn't do expansion for y minus x, okay? So we keep it y minus x bracket square plus 6y minus 6x. Why do we do expansion here? Because we have a line term, okay? So it will be, for the requirement of the question, it is like this, okay? So let's check whether we can get it. So plus 2x minus 2c equals 0. So finally, it is y minus x squared plus 6y, and then plus 4 minus 4x minus 2c equals 0, okay, equals 0. Okay, so we get the required solution, okay? So this is example 12. It is not difficult, okay, in this section.